All right, welcome to MBSI Python Coding Workshop 5, the last workshop. Okay, so we'll start off with some revision questions. So, which of the following is a correct way to import the random module and call the function that generates a random float between 0 and 1? So just put A, B, C, or D in the chat if you can. All right. So the correct answer is actually C. So D was wrong because that is an integer, not a float. So, yeah. So what will be the output for the following block of code? It's actually 5 for this one. So this is going back to like local and global variables. So the first assignment of x equals 5 is a global variable. So that will be applied when we do the print x at the end, but the x equals 20 within the function is a local variable. So that isn't applied outside it. That's why it's 5. All right, now we get started with today's content. So we're starting with data structures. So what is a data structure? Data structures are a way of organizing and storing data so that they can be accessed and worked with efficiently. Generally, data structures can be divided into 2 categories in computer science. So we have primitive and non-primitive data structures. Primitive data types such as integers, floats, booleans, and strings are the simplest forms of representing data. Whereas non-primitive data types are more advanced. They generally contain multiple primitive data elements within a more complex data structure, and they have a wide range of applications, which we'll see throughout today's workshop. We have already seen primitive data structures in previous workshops, and today we will learn more about the non-primitive data structures, which are lists, tuples, sets, and dictionaries. Sequences are a fundamental type of object in Python. So a sequence is essentially a numbered set of elements. The most important types of sequences in Python are strings, lists, and tuples. So lists are the most versatile sequence type. They have a wider range of applications than the data types we've seen so far. For example, you might want to store a list of numbers that you want to plot, a list of patients visiting a hospital, a list of medications, a shopping list, a guest list, and so on. So lists are mutable, which means that elements can be reassigned or removed and new elements can be inserted. Tuples are like lists, but they are immutable, so they can't be changed. And strings are a special type of sequence that only store characters. Note that lists are enclosed by square brackets and tuples are enclosed by round brackets. So a string is a sequence of characters and each character has an index. Note that the indexes start from 0. This is an important concept to understand, as a very common mistake is being off by 1 when indexing. For example, when trying to access or edit a specific character. Also note that the space between MBSI and workshops is considered a character and receives an index. So indexing is used to access a specific element within a sequence. Whilst I'm using the example string in this case to show you, these operations can also be applied to other sequence types. You can see that adding square brackets with an index number allows you to access a specific index element within the sequence. However, if you use an index outside the range of the sequence, you will get an index error. So the length function can be used to determine the length of a sequence. Here, the length of our string is 14 characters. So it's worth pointing out that the indexes range from 0 to length -1. So sequences can also be indexed from the right using negative indexes. Note that the indexes now range from negative length to -1. This can be useful to quickly access the last element of a sequence without having to first find the length. But the last element could also be accessed using what we learned before about the last index being the length of the sequence -1. So slicing can be used to not access one element but multiple, so a subsequence. It is very important to remember that when slicing, the start index is inclusive, but the end or finish before index is not inclusive. For example, if we were to put in example string 1:3, this would actually slice from the first to the second index. The third index would not be included in the subsequence. This is seen in the first example here, where we get BS instead of BSI. And note that when you leave either the start or the end index blank, it would default to index 0 for the start and index length -1 for the end. Also notice that going outside the range of the sequence did not cause an index error when slicing like it did for indexing. There also won't be an error if you have a start index that's higher than the finish index. You would just get an empty string. So you can also add a step size and direction when slicing. Note that if you slice in the reverse direction by using a negative step size, you want the start index to be greater than the finish index. And you can use -1 as a step size to reverse a sequence, as seen in the second slicing example. So I've shown you indexing and slicing on an example string, but these operations can also be used on other sequences, such as lists. We've seen concatenation with strings before, but again, this can be applied to any sequence. So here, two lists are concatenated together to form one list with all the elements from the two concatenated lists. We have also seen repetition with strings before, but this can be applied to lists as seen in the example. Note that there is only one list as an output. It is merely the elements that are repeated. So the in operator can be used to check if a given element or subsequence exists within a sequence. So note that this is case sensitive, so we get false for the lowercase w. All right, so the length sequence I've shown you before, but this can be used on lists as well. So note that the length function counts the lists within the list as one element. It doesn't count each individual element within the nested list. So that's why you get 5. It doesn't count one list section and 0.5 as 3, and it counts it as 1. So index can also be used to find the first occurrence of an element within a sequence. To avoid the error from the index function, you could use an if statement with the in operator that we learned on the previous slide. And this is something that will be shown in the worksheet. We can see that the index of string within my sequence is the first occurrence within the sequence. The count function returns the number of occurrences of an element. So note that the function here returns 2 occurrences of the element 2 in my sequence, even though one is an integer and one is a float. It also doesn't return an error if an element isn't within the sequence. It just gives you a count of 0. So the min and max functions can be used to return the smallest or largest elements in a sequence. You can compare between ints and floats, or you can use, or you can compare a string with a string, but you can't compare between a number and a string, or a nested list and a number. You'll get an error. Okay, now list operations, as mentioned, lists are the most versatile sequence. So they have some operations that are valid for lists that we haven't seen for strings before. So we can do multiple indexing, as lists can contain other sequences nested within them. So for example, you can have a list inside a list. You need to be able to access individual elements within the nested sequences. So this is done with multiple indexing. So most commonly, this is just double indexing, where the first index is used to access the nested sequence, and then the second index is used to access an element within that sequence. For example, here I've used double indexing to access the string listception within a list. Note that you can also use slicing when using multiple indexing. So list mutability. List elements can be inserted, removed, or replaced, and this is not possible with tuples. Note that the append method adds an element to the end of the list. You can't specify the index which you want to add an item. If you want to add an item at a specific position, you need to use the insert method instead, which also takes an index argument. You can replace or edit an element using indexing. Since we already learned about indexing, this is pretty self-explanatory, so I'll just show an example here. So here we have replaced the number 3 at index 2 with the number 0. All right, the remove method can be used to remove the first occurrence of any item in a list. The remove method will throw an error if the item is not in the list. So the remove method can remove items of any type. In this example, I've removed the string bill. The pop method can only be used on integers. However, unlike the remove method, pop actually returns the removed item, which lets you obtain the item so it can be assigned to a variable. For example, you could write x equals mylist.pop. So using pop with no argument removes the last integer by default. Whilst the pop method can be used to remove an integer at a given index, it is limited to integers. So the del function can be used to delete an item of any type from a specific index. So in this example, I've removed the string at index 1 from the example list. As its name suggests, the clear method can be used to completely clear the contents of a list. You need to be careful when creating copies of a mutable object because it is very easy to have unwanted changes being applied. For example, if I created a second list called list2 by typing list2 equals list1, then Python actually thinks they're the same object. So if I mutated either list, then the changes are applied to both. In this example, I've only appended 44 to list2, but you can see that it was also appended to list1. This is something to be cautious of. So to avoid this, you can use the copy method, which allows us to create a copy of a mutable object that is not susceptible to these issues. So we can now edit the copy while preserving the initial list. In this case, list 1 is preserved when we make changes to list 3. You can see that when we assign the contents of list 1 to list 2, Python recognizes them as the same object using the is operator. So that is why the changes made to list 1 are also applied to list 2. However, whilst list 3, which is generated with the copy method, has equal contents to list 1, it is not recognized by Python as the same object. So we can edit list 3 while preserving list 1. So two different functions, sorted and sort, can be used to sort a list into ascending order. An important difference is that this sorted returns a new list, whereas sort mutates the list it is applied to. This is because sort is a method while sorted is a standalone function. So this means that sort can only be applied to lists and has to be formatted in the way that's shown. So example dot sort. So sorted can also be applied to strings and will return a list of the characters sorted in alphabetical order, but sort will return an error if applied to strings. So here is a more comprehensive list of the methods that can be applied to lists. We'll provide a link to this in the worksheet. Dictionaries are used to store data in key value pairs. So you can see that dictionaries are written with curly brackets, with values separated from keys by a colon and items separated by a comma. So keys have to be either a primitive data type, so an integer, float, boolean, or string, or a tuple. So a tuple is the only non-primitive data type that can be used as a key. So you can't use a list, set, or another dictionary. But values, however, can be pretty much any data type. So you can have lists or even other dictionaries as values. You also can't have duplicate keys in your dictionary, so a key can only appear once. Dictionaries and the use of key value pairs are useful in a number of applications. This is really just touching the tip of the iceberg, but I've shown a simple application here where I've counted the number of occurrences of each nucleotide in a strand of DNA and stored each count in a dictionary. Benny will cover for loops next, so that stage of the code will make more sense after his presentation. In this example, the nucleotides are the keys and the counts are the values. So we saw with sequences such as lists that we had numbered indexes, but dictionaries can only be indexed using a key to obtain the value paired to the given key. If you try to index a dictionary using numbered indexes, like we did with sequences, you will get an error. In this example, the keys are the patients and the values are the conditions. But I've made an error, and it turns out that Amy doesn't have ligma. She has COVID-19, so I have to update this info. We can do this in a similar process to what we saw with lists. So I can just do conditions Amy equals COVID-19. And then we also want to add a new patient called Michael who has Parkinson's disease, and we can do this pretty much in the same way that we just did before for Amy. So the process is pretty much the same when updating an item or adding a new item for dictionaries. So we saw the del function earlier for lists, but it works in a similar way for dictionaries. Note that we only put in the key when using the del function, even though we are deleting the entire item associated to that key. So you can check if a key is in a dictionary using the in operator. You can access the keys, values, and items as shown. So using the in operator will only return true for keys, not for values. So if you want to check if a value is in a dictionary, you have to use the values method. So the elements of a set have to be a primitive data type, but you can mix different primitive data types. So for example, you can have both numbers and strings within a set. However, the important thing about sets is that they only contain unique values. Sets can be useful for finding intersections and unions, as shown in the example here, where I've used sets to find the intersection, union, and difference between two sets of numbers. So here is a summary of the non-primitive data structures that we covered today. Note that lists and dictionaries are the most useful data structures for most practical applications. You will gain experience with these data structures and see some simple applications in the worksheet. Okay, and Benny will now cover the topic of for loops. So I'll just stop sharing my screen and Benny, you can take over.
All right. Thanks, Jimmy, for introducing the data structure. And for now, I'm going to teach you guys the last content for today's workshop, the for loop. Comparing to the while loop we taught in workshop 3, the for loop has many advantages over the while loop and is hence used a lot more frequently. For example, while we use the while loop, we need to be aware of a potential risk of infinite loop. Conversely, with using the for loop, it is literally impossible to get infinite loop, and I will tell you why shortly. Before we get started into learning the for loop, let's have a revision of while loop first. We have the word while at the very first of our first line, followed by a Boolean condition. If the condition is true, they execute the body of while loop, the instruction, and hence it goes back to the condition again. The while loop will keep executing as long as the condition is true. If it is false, it stops and exits. Comparing the syntax of the for loop beside, we replace the while with a for and the Boolean condition with an item in sequence. For loop is to repeat the same chunk of code for each item in a sequence. A sequence or an iterable is any Python object that can return its members one at a time, allowing it to be iterated over in a for loop. The length of the sequence specifies the total number of iteration of a loop, and the item is an iterator variable, which is updated each iteration to store the value of the corresponding item in the sequence. So iterator variables can also be used within the body of the for loop. And here's the general form of the for loop. It's for item in sequence followed by a comma, and the next line is the instruction, the body of the for loop. And see the flowchart on the right. For each item in the sequence, if the last item is not reached, it moves on to the body of the for loop. And the loop will keep going until the final item is in the sequence is reached. If you say yes, the last item is reached, we exit the loop. We can use for loops to circle through items in a list rather than processing them individually. These two examples also show you guys how an iterator variable can be used inside the for loop. For the first example, the letter I in the first line here is the iterator variable, and the sequence, which is a list containing integers from 1 to 5. The instruction here, we have a print function, which means using a for loop to print the items sequentially. Let's say in round one, the first iteration, when I is equal to 1, we have current I is 1. In second iteration, when I is equal to 2, we have current I is 2. And when I is equal to 3, 4, and 5, and current I is 3, and 4, and 5 respectively. Similarly, if you set a sequence to be a string, hello, it comes up with letter H, letter E, L, and O. We can also use loops to circle through a dictionary by using the dictionary keys as iterator variables. We can then access the values of the dictionary using the keys. In the example, we used a for loop to print out the key A, B, C, and values X, Y, Z pairs in a dictionary named mydict. The values of the dictionary are accessed with the syntax like this: mydict with followed by the square bracket and a key inside. And hence we have this output. And I'm now going to introduce the range function, which is used commonly with the for loops. The range function generates a sequence of number, specifically the integers. Similar to when we talk about slicing list, the sequence stops before n. And we can also specify the starting value and the step size if you don't want to use the default values of 0 and 1 respectively. And in our first example, the range 6, we have n equal to 6, so the sequence starts from 0 and ends up at 5 with a step size of 1. And in our second example, the range 1, 7, 1, we have a sequence from 1 to 0, to 6, sorry, with a step size of 1. More examples. In the example on the left, we have used range function to produce a sequence of numbers starting from 0 and incrementing by 1 up to 4. And in the example on the right, we have specified starting value of 1 and kept the default step size of 1. The sequence generated goes from 1 to 5. And remember, the sequence generated by the range function stops just before the n value inside the brackets. So the example 1 stops at integer 4, and example 2 stops at integer 5. So here's the first question for the for loop content. What is the output for the following for loop? All right. Yep. The correct answer is 1, 3, 5, 7, and 9. We have a starting value at integer 1 to an integer of 10 with step size of 2. So we have 1 to 3 to 5 to 7 to 9. The second question, comparing these two loops, is there any difference between the outputs with using the range 0, 7, 7, 1 instead of the range 7? The answer is no difference. The two loops both return 0, 1, 2, 3, 4, 5, and 6. As the range function in two loops both have a starting values from 0 to 7 with a step size of 1. Right. We can also using the range function to count. In this example, we have used the range function and a for loop to print the string hello world 5 times. So in the first iteration, hello world, second iteration, hello world, to the fifth iteration, hello world. Another important use for range function is indexing. In the example, we have created a list of strings representing the first 6 letters of the phonetic alphabet. The length of the list is 6, as shown by the output of the length function here. And we can then pass the length of the list into the range function to create a list of indexing, representing the position of each entry in the list. So it should return 0, 1, 2, 3, 4, and 2, 5 in the list. We have come across the concept of nesting before in workshop 3. So similarly, we can put loops inside loops. The inner loop is executed for every iteration of the outer loop. In this example, first iteration of the outer loop prints the letter A, followed by the digits 1, 2, and 3 for each iteration of the inner loop. For the second iteration of the outer loop, it prints the letter B, then circle through the digits again. So we have B1, B2, and B3. And for the third iteration of the output loop, it prints C and circle through the digits again before exiting both loops. Here's a summary table going over everything we have covered about the loops. In the second column here, we have a syntax of while loop above. And whenever a Boolean condition is satisfied, we execute the instruction. And the for loop here, we have its syntax above as well. We need to set the item and sequence with using the for loop, which means we need to know exactly how many times to run the loop. If you don't know how many times to run the loop, we use the while loop. But remember, you do know when to stop the while loop, otherwise an unexpected result of infinite loop will be occurred. So in most cases, we know that the times to run, so therefore we use for loops. So that's why I say at the beginning of this workshop that for loops are used more often than the while loops. Okay. If you want to learn more about coding, we are making a resource list for self-guided learning. And it contains the links to the website, courses, and cheat sheet we have found useful. And the list will be posted on MBSI Coding Workshop Facebook page. And feel free to post any question to our Facebook group if we need some guidance. And it is our breakup time. Don't forget to fill out the feedback form and have fun, enjoy the worksheet.